All right, let's talk about the hidden rules that run the world around us. We're going to uncover a super powerful math concept. It's called a correspondence relationship. And trust me, it's way simpler and honestly more fascinating than it sounds. So instead of just throwing a boring definition at you, let's start with a little puzzle, just to get our brains warmed up, you know? Okay, so here's the puzzle. If one circle matches up with three squares, how many squares do you think would match up with four circles? Go on, take a second, see if you can spot that hidden pattern. And if you said 12, you absolutely nailed it. See, the hidden rule here is just multiplication. For every single circle, we have three squares. So for four circles, you just multiply 4 by 3, and you get 12. Simple, right? Every time you add a circle, you add three squares. It's a perfectly consistent, predictable change. Believe it or not, you just solved a correspondence relationship problem without even knowing it. So now that you've got the feel for it, let's actually put a name to what we just did. So this is the big idea, a correspondence relationship. All it means is that when one thing changes, another thing changes with it. And it does it in a consistent, totally predictable way. That's it. It's just like our circles and squares. One number goes up, and the other one follows a specific rule. No surprises. And what's really cool is that this is a two-way street. You know, if you're looking at it from the circle's perspective, you multiply by 3 to find out how many squares you have. But if you start with the squares, you just do the reverse. You divide by 3 to get back to the number of circles. It works perfectly in both directions. Okay, so we've got the hang of this in plain English. Now for the fun part. Let's take these ideas and translate them into the super powerful language of math, using symbols. Let's look at a new one. Think about cars and wheels, right? One car, 4 wheels. Two cars, 8 wheels. 3 cars, 12. You see where this is going? So what's the hidden rule this time? Yep, you got it. It's multiplication again. Now, turning that pattern into an actual math equation might sound complicated, but I promise it's not. It's really just 3 easy steps. First, you just say the rule out loud, in words. Second, you give your items little nicknames, symbols. And third, you just write it out as an equation. That's the whole process. Let's do it right now with our car example. Okay, step 1. The rule in words is the number of cars multiplied by 4 equals the number of wheels. Got it? Step 2, let's give them nicknames. We'll use a circle for cars and a triangle for wheels. And finally, step 3, bam! Circle times 4 equals triangle. Just like that, we've created a powerful formula that works every time. All right, I think we've totally mastered the basics. So let's put our new skills to the test. We're going to tackle a classic puzzle that actually combines a couple of the ideas we've been talking about. So here's the challenge. Imagine you're setting up tables for a big dinner, all in one long line. The question is, as you keep adding more and more tables, how many chairs are you going to need? The whole trick is to see that the number of chairs changes depending on how many tables you put down. Now, there's this really cool strategy for this, sometimes called the secret method or something like that. And it's all about breaking the problem down into 2 pieces. First, you find the part that never changes. We call that the constant. Then you find the part that does change every time you add a table. That's the variable. In our puzzle, the constant is the 6 chairs on the very ends of the long table. And the variable, that's the 2 chairs that get added with every new table we stick in the middle. And if we look at it in a table, the pattern just jumps right out at you. One table means 8 chairs. Add a second table, now we're at 10 chairs. A third table gets us to 12. You see that? It's so clear. We're just consistently adding 2 more chairs for every single table we put in the line. Okay, let's put this all together and build our final rule. We start with our constant, those 6 chairs on the ends. Then we add 2 chairs for every table in the row. So if we use symbols, it's 6 plus, let's say a heart for tables, times 2 equals a square for the total chairs. And with this formula, we can figure out the number of chairs for any number of tables you can imagine. Pretty cool, huh? Now, I know this might feel like a pretty simple idea, maybe something you'd learn in elementary school, but what we've just uncovered is actually the foundation for some way bigger, much more complex ideas in math. This is where it all starts. This whole idea of a correspondence relationship, it's the key that unlocks other concepts. Like, for example, direct proportion. That's just when 2 things grow together at a steady pace. And it's also the key to its opposite, inverse proportion, which is when one thing goes up, the other thing goes down. It all comes back to this one simple idea.
And when you put them side by side like this, the difference is crystal clear. Look at the direct proportion. As x gets bigger, y gets bigger right along with it. But check out the inverse proportion. As x gets bigger, y actually gets smaller. They move in opposite directions. But you see, both of them are just special kinds of these correspondence rules we've been playing with this whole time.
And here's the thing, these rules aren't just for math problems in a textbook. They are literally everywhere. It's the rule that decides how much you pay for apples based on how much they weigh. It's the rule that connects how fast you drive to how long it takes to get somewhere. So I'll just leave you with this one thought. Now that you know how to spot these patterns, what other hidden rules do you think are running the world all around you?